Hi there. Are you interested in winning the lottery? Then let me tell you, this video is not for you. This video is not about winning the lottery, okay? I've done enough videos with lottery in the title only for people to be mad at me for not telling them how to win the lottery. This is about computer science research, and very unfortunately the author of this paper has decided to put this word in the title. So if you're here because you want to win the lottery, this is not for you. It's something completely different. For everyone else, today we're looking at the hardware lottery by Sarah Hooker of Google Brain. This paper it's kind of a mix. It's part of a historic look back at hardware and software developments in machine learning, and it is an analysis of kind of the current situation and an outlook and sort of an opinion piece of the way forward and how hardware and software should mix and what we should focus on in the future. So the basic principle is quite simple in this paper. It introduces this term, the hardware lottery. This essay introduces the term hardware lottery to describe when a research idea wins because it is compatible with available software and hardware, and not because the idea is superior to alternative research directions. Okay, so right off the bat, I think this is a statement where I think many people can agree, or I think almost everyone will agree with this statement to a certain degree, but certainly to a high degree, right? We are all aware that, of course, we have the hardware we have. Hardware is very inflexible, it's expensive to develop, and so on. So any sort of software development, any algorithmic development may simply succeed because it is suited to the hardware that we have. So that was my first reaction when I read this paper. It's a very gut feeling of, yes, of course, this is the case. But then the historic analysis is also nice, but I was wondering, is there a deeper reason to kind of go into this? And we are going to see some pros and cons that I think in this paper right here, where I'm not exactly entirely sure what specific point it's trying to make. The overarching point I completely agree with. The fact that, of course, what hardware is here is important and may lead to certain ideas succeeding, but I have trouble with the narrower points, and I'm going to try to illustrate this in this paper while also telling you what the paper says. So first of all, here the term is called the hardware lottery, but off the bat you already see that it says a research idea wins because it is compatible with available software and hardware. So the hardware lottery right off the bat means that also the software is there. So it's technically the hard and software lottery. And the bigger question I would have to someone arguing that really the hardware lottery is an important concept to have is what distinguishes the hardware lottery? Let's even say it's just hardware. What distinguishes the hardware lottery from any lottery? Like, why can't I say, okay, there's the X lottery, and the X lottery is any circumstance that surrounds a research idea, right? Here you have idea 1, idea 2, idea 3, and they all depend on many circumstances, and X is one of those circumstances. And it just so happens that the circumstance in the world favors idea 2, and a different circumstance would actually favor idea 1. What's so special about hardware other than it's more expensive than software, right? To illustrate this further, let's say, okay, you have hardware, and you say, well, hardware is expensive, but then again, you can sort of build a hierarchy where, okay, down here there's like ideas, they depend on software, like software frameworks that we have, such as TensorFlow, PyTorch. These again depend on particular hardware. But And you can say, okay, the hardware is much more expensive, so we are not as flexible, and the ideas might just succeed because of the hardware. But then you can go even a step further and say, well, up here is sort of the consumer. If you don't like the market term, then maybe say the society, the end user, and so on. Because the hardware ultimately is directed towards what humans in society need. And that changes over time as well. So, and it's way more expensive to change the needs of human society than to change the hardware. So I can just also claim, okay, X is now society. So the one particular research idea down here might win simply because it is more suited to the current societal needs. And that kind of carries over, and you might say, well, doesn't that make it a good idea? Doesn't that make it preferable to idea 2 preferable to idea 3 over here that would just optimize for a different society? Which leads us to the question, what does it mean to, first, what does it mean to win? Here it just says a research idea wins, and you might have an idea. So I have an idea. It's not clearly defined here, but maybe winning means that a lot of researchers actually research in that direction. And the other question is here, and not because the idea is superior to alternative research directions. And here my question would be, what does superior mean? What does it mean for an idea to be superior? As I said here, certainly if an idea is more in congruence with current societal needs, you might claim it's superior. And someone else might say, well, if societal needs were different, then a different research idea might be suited better. The same way someone could say, well, if hardware was different, then a different research idea might be better. Maybe you can say if hardware was different, a different research idea might be better suited to the current needs of society, but then I'm pretty sure I can go 2, 3, 4 levels up here again. So these terms are a bit vague. I think we can all, the initial sentiment when reading this is absolutely in favor, right? I absolutely agree. I don't want to trash this. I just want to sort of, I try to think a bit deeper about what is actually said here, and this is where sort of my troubles start. So let's dig a bit into the historic part, and I think the point the paper is sort of trying to make is that that there are specific hardware choices that were made at one particular point, and because it's so expensive to change hardware, that means that a lot of researchers simply go along with whatever ideas work on that particular hardware that's available, and other research ideas are neglected simply because the hardware isn't available. Which, again, this is a sentiment that I think we can all agree with. So the first part here, the paper is in the following sections, and this is been important to keep in mind as a red thread, because I feel one can get lost in the details of the paper. So in the first section, section 2, we ask, what has incentivized the development of software, hardware, and machine learning research in isolation? We need to read this first. This essay begins by acknowledging a crucial paradox. Machine learning researchers mostly ignore hardware despite the role it plays in determining what ideas succeed. So the argument is that we develop ideas independent of hardware, but also we don't. It kind of makes a double point. It says that we just think about ideas, but the ideas we might think about may be shaped by the hardware that's available, and if we're not aware of that, we might not see other ideas as viable. So section 2 asks, what has incentivized the development of software, hardware, and machine learning research in isolation? So where does this come from, that we don't think about the hardware that's at the end? Section 3 considers the ramifications of this siloed evaluation with examples of early hardware and software lotteries. So this is the kind of historical look back. then today the hardware landscape is increasingly heterogeneous. This essay posits that the hardware lottery has not gone away, and the gap between the winners and the losers will grow increasingly larger. So this is a point that the paper basically makes, that this hardware lottery has not gone away. So right now we are in this hardware lottery, and it does so specifically with regards to saying that chips like GPUs and TPUs and even more specialized chips are optimized to neural networks. And that's why the whole world sort of over focuses on neural networks right now and discards other research ideas. And the gap between the winners and the losers will grow increasingly larger, meaning that the research ideas that are seen as inviable now, if we develop even more hardware into the direction of neural networks, those research ideas will become more and more inaccessible to the community. Then lastly, sections 4 to 5 unpack these arguments, so the ones that we've just seen. Section 6 concludes with some thoughts on what it will take to avoid future hardware lotteries. All right, so section 2 here is this sort of historic look back, and it goes from these, the point is here separate tribes. So the point is that something has made it such that the communities, the software communities and the hardware communities and the idea, let's say the idea communities, the researchers in AI algorithms, let's call them the algorithmers, they don't think that much about each other. And it makes the case that early machines were super duper specialized. Early machines were single use, were not expected to be repurposed for a new task because of the cost of electronics and the lack of cross-purpose software. So early machines, early computing machines were just single purpose and so on. But that all changed when the whole world focused on sort of general purpose CPUs that could execute any instructions, of course, according to Turing machine or von Neumann architectures. So the point that the paper makes is at some point a shift happened. The general purpose computer area crystallized in 1969 when an opinion piece by a young engineer called Gordon Moore appeared in Electronics magazine with the apt title Cramming More Components Onto Circuit Boards. That's a cool title. So this famously gave rise to Moore's law. Moore predicted you could double the amount of transistors on an integrated circuit every 2 years. And this sort of held true. Where people stopped building people stopped building special purpose hardware, but invested just more and more and more into building these general purpose chips, these CPUs, and the reason why they stopped making specialized hardware is any specialized hardware you build will simply be surpassed by the next generation of CPUs. So even if you make a specific purpose hardware for some problem, you just have to wait like 1 or 2 of these cycles, and ordinary general purpose CPUs will simply will overtake your specialized hardware. And since CPUs are general purpose, the market for them is naturally huge. So this has made it such that what was mainly developed was general purpose CPUs. I think the paper wants to make the point, though I'm not exactly sure. I think it wants to make the point that even though the CPUs might be called general purpose, they aren't general purpose. Like, they have their specific advantages and disadvantages, and that's going to hurt, for example, neural networks in the years following this. So in conclusion to this chapter, they say, in the absence of any lever with which to influence hardware development, machine learning researchers rationally began to treat hardware as a sunk cost to work around rather than something fluid that could be shaped. However, just because we have abstracted away hardware does not mean it has ceased to exist. Early computer science history tells us there are many hardware lotteries where the choice of hardware and software has determined which ideas succeeded and which fail. And the example is kind of the Charles Babbage's analytic engine that Charles Babbage designed, but was something like 50 years earlier or so than parts could even be manufactured for this idea to succeed. And we know many stories of these people being ahead of their time, and they have this interesting quote, I think, somewhere from Silicon Valley here: being too early is the same as being wrong. And this paper, of course, focuses on hardware. But to come back, the conclusion of this chapter is that because of this general purpose area, because the entire focus was on building general purpose CPUs, this has led to people not really having an integrated thought of hardware, software, algorithm, but treating hardware as this thing that can execute any instruction, and then the algorithm comes on top of this sort of black box that we can't really change. We just have the hardware we have. Yeah, which comes back. And again, I'm not sure. Like, sure I agree that the entire world focusing on general purpose CPUs has some influence, but certainly hardware is just expensive to make. So you could argue that even if this hadn't happened, a machine learning researcher wouldn't necessarily think about the hardware, but they would at least have a choice if there were a selection of hardwares, right? Okay, so that was the section 2. Section 3, now we really go into the historic evidences, and there are kind of early historic evidence, like this Charles Babbage's machine that he invented. An early example, the analytical machine in 1837, and no, it wasn't even decade. It was only surfaced during World War II. In the first part of the 20th century, electronic vacuum tubes were heavily used. This is, I've noticed a number of typos in the paper. I realize it's a preprint. If the author is listening, I can also make a list, but this one just popped out. For radio communication and radar. During World War II, these vacuum tubes were repurposed to provide the compute power necessary to break the German Enigma code. So it would be long after, not only after Charles Babbage invented this machine, but even after he died, that people would sort of retake and in some parts reinvent his ideas to build modern computers. The big example, though, that the paper makes is what it calls the lost decades. And this is the story of neural networks coupled with two things, with an AI winter and a focus on expert systems, and maybe also, though that's not entirely mentioned here, a focus on things like SVMs. So I think it's widely known that the main ingredients for neural networks are very, very, very old. So here the paper gives some examples. Backpropagation invented in 1963, reinvented again, and deep convolutional networks paired with backpropagation by Yann LeCun. It says, however, it was only 3 decades later that deep neural networks were widely accepted as a promising research direction. I think this sort of the timeline here is, this here probably refers to around 2010. Shortly after that, of course, AlexNet beats ImageNet and so on, but even earlier, a bit earlier, people were doing heavy research into neural networks. And 3 decades later, so this is paired with kind of these numbers right here, let's say 1970, 1980, when these ideas were invented, presented, but computers back then were simply unsuited to run neural networks. Here it says, the gap between these algorithmic advances and empirical success is in large part due to incompatible hardware. During the general purpose computing era, hardware like CPUs were heavily favored and widely available. CPUs were good at executing any set of complex instructions but incur high memory costs because of the need to cache intermediate results and process one instruction at a time. This is known as the von Neumann bottleneck. The available compute is restricted by the lone channel between CPU and memory along which data has to travel sequentially. So the paper goes on and says there were some efforts into specialized hardware for neural networks, but funding was kind of not there, and other specialized hardware was more into the direction of popular ideas then, like Prolog and Lisp, which could do expert systems and not necessarily neural networks. And only it would take a hardware fluke in the early 2000s, a full 4 decades after the first paper about backpropagation was published, for the insight about massive parallelism to be operationalized in a useful way for connectionist deep neural networks. A graphical processing unit was originally introduced in the 1970s as a specialized accelerator for video games and developing graphics, yada yada yada. GPUs were repurposed for an entirely unimagined use case to train deep neural networks. Had one critical advantage over CPUs: they were far better at parallelizing a set of simple, decomposable instructions such as matrix multiplications. Multiples. Multiplications. Multiples? I don't know. So the point here is that the ideas were around for a long time, but it would take GPUs to make them work. And so the image that the paper builds up, I think, is that you have these, you're here and you research, and then you have a decision to make. Which hardware do I build for the future? And there are 2 directions. This is direction 1 and this is direction 2. And let's say for whatever reason, direction 1 is chosen, okay? Then because it's so expensive to build different hardware, the world largely goes with direction 1 and builds on top of that, okay? So that also means that all the research ideas that profit from direction 1 will appear to be much more effective than research ideas that would have profited from direction 2. And it sort of says that neural networks are over here, and it's sort of the let's say the other systems, what do we give, expert systems, let's call them expert systems, and other types of ideas were over here, and they appear to work really well until they stopped in progress, and then by accident, sort of, this road here was traveled with GPUs, so it was not obvious, but by accident, still this was developed, and then neural networks could flourish. And if it wasn't for that fluke, if it wasn't for video games, basically, or animation, we would have never known that neural networks work as well as they do. So again, that's the point the paper makes, and I think we can all agree with that particular point. But I want to, again, I want to build up sort of a different picture right here, in that why is only, like, I feel hardware is considered a bit much here. So I think you can make the general case that at any junction you have several things you can choose, and then once you choose a thing, all the things go in that direction. Like new ideas will be more in that direction. Also new hardware will be more in that direction because a lot of people research on it. The paper also makes the point there's kind of this feedback loop. But let's say neural networks were down here. What I would argue, and this is a bit of a point the paper makes in a half formulated way, I think, is that it basically says that had we invested in matrix multipliers, in GPUs instead of CPUs in these early years, that means that neural networks would have sort of succeeded as an idea at that time. And I'm not entirely convinced of this, because first of all, you can see right here, GPUs were actually around in the 1970s. So the hardware was available. It's not like it was super easy in 2010 for these early researchers to build their code into GPU compatible code. That was certainly hard, especially if you read the papers, but it would have been hard in 1970 as well. It would not have been significantly harder, I think. So I'm not sure if the picture is really like this, or if the picture, so if this is the CPU direction, is more like that neural networks are actually somewhere up here. And the fact is we actually needed the good CPUs in order to develop in order to make use of the GPUs, right? And this here would be GPU, in order to make use of the GPUs to then enable these neural networks on the GPUs, because certainly it has helped a lot that CPUs were built, that computers just built on GPUs would be sad computers. Computers built on CPUs are cool. They can do multiprocessing. They can do internet. They can do most of the video game except display the graphics. And very arguably that without the heavy focus on CPUs, we would not have neural networks today, even if we had invested all of that effort into building GPUs. Because society has just advanced so much because of CPUs. So I'm sort of tempted to challenge this notion here that just because of the happenstance that CPUs were advanced at that time, that neural networks didn't have their breakthrough back then. I think we needed both. That being said, I do agree with the paper that we might have never ever realized that neural networks worked if it weren't for the fact that there is specialized hardware around. So that would be my points to this. The paper makes this point about, okay, there is hardware lotteries, and so now it also introduces software lotteries, though it said at the beginning that hardware lotteries included software, but I'm going to guess that the general concept of a lottery was simply presented. And again, I don't see exactly what's so special about hardware, because again, I can make the same case for software. It's just a shorter time frame. I can make the same case for theory, right? Like whatever. Now neural tangent kernels are the hit, right? Everyone's like, wow, NTKs, blah, 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 blah. Who knows, right? But some big names announced this, and some theory has been done in this direction. And because there is already a big momentum, lots of people publish in it. Who knows if that's a good idea, or if there were other ideas that, had we done the fundamental work in these, would flourish right now. I agree with the sentiment, and I don't see why the hardware is such a special case right here. So the next thing that the paper looks at is kind of the current day. So it tries to make the point that we might be in a hardware lottery right now. And again, the intuition, of course, is yes, of course, we have the hardware we have. It's difficult to change, especially since hardware builds upon hardware. With the tree I drew before, let's draw it again. You draw a tree, and literally every decision you make in the tree, and this doesn't only need to be hardware, right? Every single decision you make will mean that pretty much all of the previous choices here are now fixed and ingrained. We build upon we build upon inventions of the past. It's impossible to go back and do all of these things again. And if you see something curious right here, and this is where we're going into later, I want you to see what happens if here is a good idea. Like, here is my super duper booper idea. And my super duper booper idea simply didn't make the cut for that choice. Like, someone chose a different hardware direction, software library direction, whatnot. It wasn't in vogue, and my idea was unpopular then. If one choice is made, this choice right here, it's hard to go back. If two choices are made, right, that build upon each other, it's even harder to go back. So as time goes on, it's harder and harder and harder to go back, which is a point that the paper will make at the end, that the difference between the winners and the losers is getting bigger and bigger, which is an effect that this idea that once was a curiosity that could be investigated becomes a very costly investigation, because we need to reinvent and re-engineer a whole bunch of decisions. And with time goes on, it's simply forgotten because there's so much that we have built past this. However, this is for the loser, right? This is the loser. However, for the winner, I disagree right here, because here it says, okay, this direction, the idea direction here, let's say there is a super cool idea that would beat the crap out of neural networks. Whatever the latest Schmidhuber paper is, that idea would beat neural networks. And this here is neural networks. And everyone's doing neural networks, and Schmidhuber's idea is just forgotten about. Now, to say that neural networks are the winner and the winners will increase and increase and increase is correct, but it forgets that right here there is this whole branching. So within the neural networks, you have again this branching, and maybe over here, what kind of neural networks were completely forgotten? Like MLPs. No, MLPs are maybe still a thing. I don't even remember, like early neural networks were 10H nonlinearities for MLPs or something like this. 9x9 filters, 9x9 filters in convolution, things like this, right? It's sort of, the 9x9 filters are technically in the class of neural networks, but as time progresses, and this branch here are the 3x3 filters, which are massively outcompeting the 9x9 filters. So the 9x9 filters are forgotten, and it could be that if the 9x9 filters, because of the 3x3 filters, now we have specialized hardware that exclusively focuses on 3x3 filters, so we go down this route, down this route, down this route, down this route. And there might have been some other super duper idea down here that only works when we have really big filters. And now we never know that this existed, right? So to say that the difference between the winners and the losers gets bigger and bigger sort of misjudges that these winners will be fractionated and fractionated and fractionated, and every push in one direction comes with costs to these other directions within that winner branch. But this is, ultimately, you have a choice. Do I want to go back and go this direction, or do I want to add something here? It might be worth more for society to go up here. The paper is going to argue at the end that we should sort of keep funding alternative directions in hardware, which I think is always a good thing, to not lock in on particular ideas, but also you sort of have to strike a balance, because researching on things that already work and make them better is a crucial part as well, because you can discard these sub-ideas that don't make any sense. All right, so it gives some examples of current hardware lottery winners. To improve efficiency, there is a shift from task-agnostic hardware like CPUs to domain-specialized hardware that tailor the design to make certain tasks more efficient. the first examples of domain-specific hardware released over the last few years, TPUs, and then it also says Edge TPUs, Cortex, ARM Cortex M55, Facebook's Big Sur, which I think is just like a box with 8 GPUs in it and some InfiniBand. Optimize explicitly for costly operations common to deep neural networks like matrix multiplies. So here I have, again, there's this double meaning. So it says here is task-agnostic hardware like CPUs, but at the same time, it argues that CPUs are particularly bad at matrix multiplies. So it's not really task-agnostic. It's just focused on different tasks. But I see what the paper means right here. We do build hardware that make matrix multiplies faster, which means that neural networks, that benefits neural networks research. Closer collaboration between hardware and research communities will undoubtedly continue to make the training and deployment of deep neural networks more efficient. For example, unstructured pruning and weight quantization are very successful compression techniques in deep neural networks, but are incompatible with current hardware and compilations kernels. Hardware and compilations kernels. I don't know what that means, but it's incompatible with current hardware. The paper argues that because we see that these ideas are good, there will be specialized hardware for them. And I think the point the paper is trying to make is sort of like, see another win for neural networks because we go down the neural network road. People focus on neural networks, focus on how to prune them and so on. Hardware will be developed, which will lock us in further into neural networks, which again is, the paper is basically saying like, look, because we went this road right here, we're going to go this road a lot more. But then what you have to see is that if we then from this road go here, because we do want to do weight quantization in this particular way, we also are going to neglect this, which would be doing some whatever other thing that we could do. Yeah. So there's always in each decision there's a branching. Undoubtedly, the paper is correct and it says the branching decides the future, but I think the focus here on hardware and neural networks versus non-neural networks is a bit, it's very specific to that thing. Then it makes the point why it matters. So why it matters? It matters because the paper says, okay, where's that? Here. In 2019, a paper was published called Machine Learning is Stuck in a Rut. The authors consider the difficulty of training a new type of computer vision architecture called capsule networks. And I kind of realized that capsule networks aren't really suited to current hardware. And he says, whether or not you agree that capsule networks are the future of computer vision, the authors say something interesting about the difficulty of trying to train a new type of image classification architecture on domain-specific specialized hardware. Hardware design has prioritized delivering on commercial use cases, while built-in flexibility to accommodate the next generation of research ideas remains a distant secondary consideration. Which is true, though I would also say, I mean, CPUs and GPUs combined are extremely general operations. Like they're very, very generalized. Okay, GPUs are good at matrix multiplies, but CPUs are good at a lot of other things. So I would say the GPU-CPU combo is a very, very, very flexible general purpose hardware design that doesn't lock you in too much. And maybe it's just that capsule networks are, by algorithmic design, way, way harder to implement. Like to build specialized hardware for capsule networks, I'm not sure if that would even be possible, and to speed them up to the degree that CNNs are sped up by GPUs, just out of the algorithmic nature of capsule networks. And I've done videos on capsule networks. They sound pretty cool, but they also sound like implementing the thing in hardware is going to be quite tough, even if you build specialized hardware. They also go into GPT-3, claiming that the paper claims that because we are kind of locked in this neural network, paradigm, in this kind of hardware, several major research labs are making this bet, engaging in a bigger is better race in the number of model parameters and collecting ever more expansive data sets. However, it is unclear whether this is sustainable. An algorithm's scalability is often thought of as the performance gradient relative to the available resources. Given more resources, how does the performance increase? And they go into examples here that you can scale up the parameters, which gives you less and less of a gain. So it's like this diminishing return over time, which it brings up GPT-3, which I find interesting because GPT-3 showed, in a way, okay, it was in log space, but it showed a fairly linear decrease in perplexity. So a log linear decrease in perplexity given more parameters, which goes a bit against the narrative of the paper. And also in terms of this definition up here, given more resources, how does the performance increase? I see the fact that you say, well, it's $12 million to train GPT-3. It says right here, $12 million to train GPT-3. On the other hand, I would say, what's the cost of, building specialized hardware to research alternative research directions? By the way, we have no idea what alternative research directions work. So the only thing we could do is fund all hardware. And if we had to fund all hardware for other algorithms, then select the ones that are promising, then invest more, and so on, $12 million will get us nowhere, which I think is a point the paper is trying to make. But from a efficiency perspective, given where we are now, it's actually more viable to build GPT-3, which, again, I think this is something the paper agrees with, but at the same time, it tries to make the point that, look, we are investing more and more and more, and we're getting less and less out of it. Maybe it's time to go a different route in terms of hardware, but that's going to be more and more expensive the more we go into this neural network direction. I'm not sure about this. Again, if you think of this tree, the paper basically tries to argue that what GPT-3 is trying to do is it's trying to make a push up here into the next, kind of push the frontier on a path that we have gone for a while. And the paper is trying to say that had we imaginarily gone a different path down here, a equally hard push in this direction would maybe yield a better result. Yes, maybe, but yeah. But the question is it, at what point does it become viable to sort of abandon this entire direction and skip and kind of start there? Because we would need to do the whole tree thing again, and then within the tree, the same logic applies. It does, though, make a good comparison to the human brain, which works fundamentally different. It says, while deep neural networks may be scalable, it may be prohibitively expensive to do so in a regime of comparable intelligence to humans. An apt metaphor is that we appear to be trying to build a ladder to the moon, sort of saying that we can't, at the rate where we scale neural networks right now, it's not conceivable that we reach human level intelligence by simply scaling them up, which is why we might want to investigate entirely different directions, and why we might want to investigate entirely different hardware choices. Yeah, which, granted, that's correct. Though I would say transformers aren't particularly suited to the hardware because they require such huge memories, and GPUs traditionally have been rather limited in memory, and transformers still kick ass on this hardware, even though memory is extremely limited compared to like CPU memory. And only now do we see GPU manufacturers focus on more memory. So you can argue from the perspective of the paper and say, see, because we have neural network hardware, now people are building more neural network hardware. But also you can say that initially a bad choice was made, sort of, but researchers still managed to demonstrate transformers would work, and now the hardware is developing in this direction, which is also a thing the paper argues at some point. Again, I have a hard point parsing out a direct point here. I think the paper is more meant to make you sort of think about the different points it brings up, which is also probably why this video is more of me rambling than anything else. So here it says that currently there are some initiatives to build other types of chips, other types of hardware and so on, but they, as well as the last ones, they might be not enough because it takes producing a next generation chip typically costs $30 to $80 million and 2 to 3 years to develop. And even that is, however, even investment of this magnitude may still be woefully inadequate, as hardware based on new materials requires long lead times of 10 to 20 years in public investment and is currently far below industry levels of R&D. This is the kind of DARPA and China who funded research in this direction. So the paper says it might be way too little. Though it also says there are a couple of good lights at the end of the tunnel, saying experiments using reinforcement learning to optimize chip placement may help decrease cost. And I think I've done a video on this paper. There are also renewed interest in reconfigurable hardware such as field program gate arrays and coarse-grained reconfigurable arrays. So this is hardware that you can sort of meta-program. So you can take the hardware and you can specialize it by programming it. And so it's like a meta-programming it. You can sort of take one of these things and make it into like a sort of a GPU if you need it like that. And then you can reprogram it, program it differently for a different application. Though, if I take the other side of this paper, I would say, well, isn't that the same thing that CPUs were? And yet still CPUs made it almost impossible for neural networks to run. Aren't you, even though FPGAs are very general, aren't you making implicit choices on the ideas that are very well suited to FPGAs, or the ideas that are very well suited to using reinforcement learning to optimize chip placement? Isn't that the exact same thing? Yeah, I guess you can make this argument at infinitum. No, infinitum is different. Okay, this video must come to an end. So the last part here says that what is also needed is kind of a software revolution, that there is a shorter feedback time, where it imagines software that tells researchers which hardware their algorithm is particularly suited, or how their algorithm would fare on different hardware, such that if you invent a new algorithm, it doesn't work on a GPU, you could sort of submit it to this software, and then the software would tell you, well, this would work really well if type X of hardware existed, and then you can maybe invest money into that rather than discarding your idea. In conclusion, yeah, the conclusion isn't very long. The performance of an algorithm is fundamentally intertwined with the hardware and software it runs on. This essay proposes the term hardware lottery to describe how these downstream choices determine whether a research idea succeeds or fails. Today, the hardware landscape is increasingly heterogeneous. This essay posits that the hardware lottery has not gone away, and the gap between the winners and the losers will grow increasingly larger. In order to avoid future hardware lotteries, we need to make it easier to quantify the opportunity cost of settling for the hardware and software we have. And my conclusion is I generally agree with this paper. I really appreciate the historic overview, but I do think the focus is, it centers too much around hardware, where I think this lottery case you can make for literally any single branching choice, and maybe you weigh that by the cost that it takes to revert or change that choice in the future. And it also focuses a lot on neural networks versus non-neural networks, where it kind of, this winners and losers thing, where it says neural networks are the winners, and if we investigate more into neural networks, then they will remain the winners because of this feedback loop. However, it kind of, in my opinion, discards the thing that within the neural networks, in the next choice of hardware, there are going to be winners and losers again and again and again, and there are going to be entire branches of neural network research that are abandoned because they don't fit the hardware choices once more. And this gap between what it's conceived the winners and the losers, it compares losers in terms of an idea that was had in 1 year to the winners, which are always reevaluated every year. So it's kind of not a fair comparison, in my opinion. And then also, no, that was it from me. Yes, I do implore you, if you are interested in things like this, as I said, this is more of a historical and opinion piece, trying to make some argument and give you some directions to think about, which is pretty cool as a change to a simple bland research paper. All right, that was it from me. Again, if you're still here waiting for how to win the lottery, this is not the video. Bye-bye. See you next time.